Professor Mosier here. I wanted to combine two different demos into one video for you because this one sensor I have uses two different technologies that may be useful to you. The one is called a rotary encoder, and the other is called a variety of things, either qwiic, stemma, or I2C. And so we'll talk about all of that in this video. First, let me talk about the rotary encoder part. So this little box on this circuit board is the rotary encoder. It's much like a potentiometer in that it's a knob that we can twist left and right, but it has some other features as well. This knob can twist a full 360 and it can just keep going and going and going. When I twist it, it has a very subtle kind of click to it, and you can kind of see how it locks into positions as it steps around its axes. So rather than measuring resistance between a voltage source and a ground on a third middle wiper pin like a potentiometer does, this outputs clicks. And we can count clicks and whether the clicks are going up or down to determine whether it's being turned left or right. So it's just a different kind of knob. A lot of times people want to use something like this in their controllers or other projects. So I thought I would show you how it works. Similar to a potentiometer, this just slides off. There's a nut and washer on here so you can attach it to a panel, just like a potentiometer. Other neat thing, if I can get this back on, is that this clicks. So if I push it, you might be able to hear that. It can function as a button too. So I can use a button and a turn in the same mechanism. Now the board that it's on is the encoder for the rotary knob. This helps me translate the click data off of this into something that's usable. With just the rotary encoder itself, it can be a little tricky to wire it up and write it up in code so that you can get usable data off it. It can certainly be done, but using a board like this makes the process much easier. And I mention this too because the protocol that this board uses is used by a lot of the more complex sensors. So there's a lot of sensors out there, 9-axis, accelerometer, gyroscope, compass modules, temperature, barometric pressure sensors, all these things that are almost micro computers in their own right in terms of the data that they are measuring and processing. And so they don't output a simple analog value like our photoresistor does, or a force sensitive resistor does, that's easy to measure with just a fixed resistor. So when we get into more complicated things, it can be helpful to use a sensor with a breakout board and a library and communication protocol that basically relies on someone else doing the hard work of getting the sensor to work, and we can just access its values then in our code and use it for what we want. So if I look at the back side of this, you can see the little chip that's doing the coding for us. It's got some pins here, some pads over here. It's got a NeoPixel on it, and then it has these two very tiny ports on either side. So how do I wire something like this up? Well, if you have one of these, you get a sensor that you don't know exactly how it works. The best thing to do is to look at see if there's any documentation provided with it. So if I look at this rotary encoder from Adafruit, you can see the soldered encoder comes like that, $8. That's a reasonable deal. Adafruit provides very good documentation for all their stuff. And if we scroll down to the Learn section here, it will give us all the information we need to know about the Rotary coder. So this is the overview, showing how to solder it. We can look at the pinouts. Power, 3.3 volts, ground. It's going to tell us about the I2C if we look back at our chip. These pads here are labeled SCL, if I can get that to focus, VN, ground, SDA. On that side, and then over here we have A1, A0, and A2. So remember that. I'm going to come back to these in a second. And so the SCL, SDA, the ground and the power are what we use for this I2C communication protocol. I2C is a 2-wire low voltage communication protocol. It allows us to put multiple sensors on a single bus and communicate them. There's the data that's being sent on the data line, and then the clock pin makes sure that the data is being received at the right rate. The address jumpers, those are the A0, the A1, A2. In the default state, it's telling us the address is 0x36. If we have multiple of these rotary encoders, let's say we wanted to put 4 of these together for an interface, the addresses would collide and conflict then. They would all, in their default state, be 0x36, and the microprocessor would get very confused about what was going on when any of them was turned. So we can solder closed those little jumpers. You see there's a little break there. So if we put solder across those, that will close that line up, which allows us to change the address. So if I solder close just the A0 one, that will turn the address into 0x37, leaving A1 and A2 open, etc., etc. Okay. So for now, we're just going to leave this one open since we've only got one, but good to know that you can put multiple of these together. You just need to change the address as you go. Okay, so coming back here, how do we connect this thing up? It's got pins on here where I could solder headers and plug it into a breadboard if I wanted to, but I'm going to use these ports that it has. These ports are 4-pin ports that replicate the SCL, SDA, ground, and power lines over here. And for our circuit playground, I'm going to use this alligator clip to qwiic cable. Adafruit calls these qwiic. SparkFun, I believe, calls them stemma, or maybe I have that backwards. Either way, it's a very small 4-wire connector that has ground, power, data, and clock, and we can just plug that into one of these ports, and that gives us access with alligator clips to these lines. If we use other boards, just as a quick example, I've got a very small QT board here that has a semi-qwiic port on it, and I've got that with a different cable that has female headers on it, connecting to this little OLED screen that works over I2C. You can get cables that are qwiic to qwiic, so I could connect this board to this rotary encoder, and they come in a couple different lengths. I2C is not a long distance protocol though, so you generally want to keep these spans of wires under 10 inches total length, or you can start losing data. So then how do I connect it up to this? Well, there's 2 things I know. I know that I want 3.3 volts for the power, and I know that I want ground for the black one. But the yellow and blue, I forget which one's data, which one's the clock. it doesn't tell me on the little block here. So I'm going to go to the website and look up I2C protocol, and here we go. Great picture. So blue is going to be blue. Here we go. Blue is SDA and yellow is SCL. So blue is SDA, SDA, there. Yellow is SCL, there. And you can see these pads are labeled SCL, SDA there. And then just to keep these all together, I'm going to move this one to that ground pad there. Okay. So now I've got my Rotary encoder wired up to my circuit playground. And then the next step is let's look at Arduino code for this. So again, the beauty of using these sensors is that we can use a library, right? We don't have to write all the code ourselves. And again, maybe I don't know what the library is for the specific sensor. So let me go back to that overview guide. If I go to Arduino, it'll show me some more ways to wire that up to different Arduino boards. And then the library I want is called Seesaw, Adafruit Seesaw. So let's see. Maybe I have that already, maybe I don't. I do. So I've got that installed. If you don't, you can install it here. It might ask you to install some other things along with it, which I would say go ahead and do. Let me wire this board up so that we can get some data. Okay. And I'm going to just look at the example for this. So if we go to examples, Adafruit Seesaw. Seesaw. Encoder basic. Okay, so let me walk through this, see what we've got going on here. We're including the libraries, one for the Seesaw, one for the NeoPixel. We're defining a couple constants. This is our address, 0x36, which is our unsoldered 3 pads, the default state. That's good, that's what we want. And it looks like we've got a switch and a NeoPixel. I'm guessing these are pins as defined by the little chip on here for that button press and the NeoPixel light. We've got 2 objects that are unique to this library. We've got the Seesaw itself called SS and the NeoPixel called SS Pixel. Okay. And we've got a variable called the encoder position, which is an int 32t type. That's just a fancy integer. Okay, in our setup function, we've got the serial port going at a high speed. We're waiting for the serial port to open. We're going to say that we're looking for the Seesaw. Then we're telling the library to begin on that address from up here and the pixel. And if neither of those, so not either of those, so if either of those come back false, we're going to say couldn't find the Seesaw. Okay, and then that will just kind of stop the code there. If it's able to find those things, instead it's going to say the Seesaw has started. We've got a version number. It's going to tell us about the firmware and the product. Then we're going to set the brightness and turn the pixel on. Okay, so within our SS object, so those are within the pixel object, within our um, seesaw object, we're setting the pin mode of that switch to an input pull up. And then we're going to get the encoder position. Seesaw.get encoder position is a function from the library that will get the click of this. And then we're doing a neat thing here with this. We're using interrupts. So these four lines have to do with setting interrupts so that when this is turned, it will interrupt our loop code, so we don't have to worry about getting locked out or missing clicks from this. Okay, so then at the top of our loop, we've got if not seesaw digital read switch button pressed. So this is interesting, and you're probably familiar with this now. But since we're using pull up, the default state of this switch button is high. So we're saying if not high. So if it's low, that means the button is pressed. If it's high, it's not pressed. So it's the opposite of an intuitive thing because we're using input pull up on that button. Then we've got a new position, so we're going to read the seesaw encoder again to get the position. Then we're going to check. This is very much like when we wrote a toggle button code. We're going to say, okay, is the old position not equal to the new position? If so, we're going to print the new position. We're going to set the pixel color to this, something based on this new position using the wheel function. We're going to show it, and then we're going to set the old position to the new position. We're going to wait a couple milliseconds so we don't overwhelm the serial port, and then go back and do it again. And then our wheel function down here is basically just changing the color of the NeoPixel based on the spin of the knob. So let's upload this and see if it works. We've got our board and port set. Here we go. Okay, let's check the serial out. Looking for seesaw. Seesaw started. Found 4991. Turning on interrupts. There we go. So we've gotten through the setup. And if we turn, we got 1, 2. You saw the NeoPixel turned on red there. 6. So we're clicking up one direction. It's turning orange. Yellow. Green. Blue. Okay. Now, so I've been turning this counterclockwise. If I turn it clockwise, you see the number starts going down. I can spin it all the way down. It becomes negative. Back up. And that is from this right here, the get encoder position. So the chip on here is keeping track of the position, and we are reading it, and we're only doing stuff if it changed. So when it's just sitting here, not turning, we don't get output. If I click the button, it gives us button pressed, and that does not have a lot of debounce on it, so it's going to give us a lot of button pressed as long as we hold it down. We can go back to twisting. So that is how you use the rotary encoders. I highly recommend, if you want to use these, that you get something like the stemma QT version that has this decoder board attached to it, and also how we can connect up the stemma QT I2C protocol to a variety of other sensors and devices, and through using libraries, access these much more complicated sensors.